We're back, and I'm going to summarize briefly where we are. Again, the overall primal dual, primal dual approach says we start from an f, which is a dual our dual solution, and then we let f bar be the so let me write it out. This is some dual feasible solution. We let f bar be a solution to the DRP. And in particular, we saw that this f bar has to be an augmenting path with all of the using as forward edges only things that were unsaturated, backwards edges only those that had strictly positive flow. And then we update the dual by writing f plus theta f bar. So again, just writing this out here, an augmenting path given a feasible flow f, given f a feasible flow, is a path from S to T in the undirected graph. So dropping the directionality, except that such that our path P uses, let me write it differently, such that any edge, an edge ij used by our path P in the forward direction has to have Fij strictly less than Bij. And an edge used by our path in the backward direction has to have Fij greater than 0. Now again, if you look at what this looks like, what our update is, this is basically natural. It's saying f bar is our augmenting path, f is our original flow. I'm going to add a multiple of f bar to f. The only way that's going to stay feasible is if I'm not increasing any of the saturated edges, and I'm not decreasing any edges that had already had 0 flow. That's all that this is saying. And so a corollary of that is that once we found an augmenting path, we can use P to augment the flow by how much? Well, I start growing theta, and I have to stop as soon as an edge is saturated, a new edge becomes saturated, or one of the edges that I was using in the backwards direction becomes drained. So we can augment the flow by some amount, let's say delta, that's equal to min over all edges used by my path of Bij minus Fij for all ij that were forward edges in P, and Fji for all edges that were backward edges. Because and you can look back at that example from the previous lecture to see exactly where this comes from. Okay, so we could stop here and basically say, just solve, rather than having to find an augmenting path using a combinatorial algorithm, just use the simplex method. That's where Primal-dual came from. But all of the story of Ford Fulkerson is in support of this idea that the combinatorialized problem is easier than the overall problem. So rather than just saying throw it into simplex as a black box, that's what the kind of most general framework of the Primal-dual algorithm does. We are going to give a the Ford Fulkerson algorithm for finding augmenting paths. So this is how this works. So this is the next several slides are going to develop the Ford Fulkerson algorithm, and it's essentially a labeling algorithm. So the way this works in kind of in words, and we'll see it in more detail, is we start from node S. This is our special node. With a label, and I'll explain what these labels are. I'll just write C next slide. So that explains what the labels are. And from S, we look at all nodes adjoining S, and we label all of those. And now we have a bigger set of labeled nodes. And now I go to each of my other labeled nodes, and I label their neighbors. And so at all times, in order to make sure I'm not doing something silly like keep going back to S, if I've already labeled all of S's neighbors, it's not going to have anything new to label. So I'm going to remove S from this list of nodes that need to be, whose label needs to be propagated. So this labeling algorithm is essentially going to keep looking at neighbors until it's looked at every single node in the graph that it's allowed to look at. So we start from a node S with a label as in the next slide, and we propagate labels. This propagating step is also called scanning. Just giving you some of the basic jargon you might see. So you scan a node means looking at all of its neighbors, see which ones are eligible to be labeled, and we move on, and we move on from there. Move on until no more nodes can be labeled. And at that point, either all of the nodes will be labeled or not, but certainly no more of the nodes can be labeled. So let me explain how we assign labels. So each node has a label with two parts, which I'll very creatively call part 1 and part 2. So node I has a label that's L1 of I and L2 of I. And L1 of I is just saying when you were labeled, what node was being scanned. Remember that we start from a node, we scan all its neighbors, and then the ones that are eligible to be labeled are labeled. Now we go to every one of those nodes, we scan their neighbors, and everyone that's eligible to be labeled, we label. Okay, so that means that you were labeled when every node I was labeled when some other node was being scanned. So so L1 of I is from where I was labeled, meaning which node was being scanned. And L2 of I is the amount of extra flow that can be brought from S to I. So let me explain with an example. Just a simple example. Here's S. So suppose that this capacity is 1, and this capacity is 1/2. And in F, my solution F had assigned a half a unit of flow here and 1/2 unit of flow there in this in the forward direction. Then, what would the label for this node be? Well, it was labeled when S was scanned, and it's already getting half a unit of flow, and so it could get another half. So the label would be S, 1/2. Now, in the next round, what would the label of this node be? Well, it was, I guess I need to label what the nodes are. Maybe I'll choose yet another color. I'll call this node 1, call this node 2. Sorry, there's just too much going on. Now looking at node 2, well, that was labeled from node 1. And what is the extra amount of flow that can be brought? And the answer is 0, because that edge is already saturated. It has capacity 1/2, and it is already carrying, and it's already carrying 1/2. Okay, so it actually can't go forward anymore. Actually, to be exactly precise, we wouldn't even have labeled that node if it were saturated. So let me make a better example. Let's suppose that this were, I don't know, 2/3. Not that this really matters. We'll see this general example. So if it were 2/3, then this 0 would be not 0, but it would be 1/2 minus 2/3 minus 1/2, which I think is 1/6. Okay, so this is how the labeling algorithm works. Let me just write it in general. In order to give me some more space, I'm going to just erase this example, and hopefully that's okay. It's in the video. Okay, so here is the general labeling algorithm. So if node I has been labeled, and I'm going to write down generically it's labeled, so just L1 of I, whoever was scanned when I was labeled, and L2 of I. And let's suppose, what are the two situations? The two situations are that I have a forward unsaturated edge. So Fij is less than Bij. If the edge is saturated, we don't label. That's why I made the capacity 2/3 instead of 1/2. If it's saturated or empty, we don't label. I'm sorry, if it's a forward edge that's saturated, we don't label. And if it's a backward edge that's empty, we don't label. So as long as Fij is not saturated, it can be 0. Then how is node J labeled? Well, L1 of J, L2 of J is equal to, J was labeled when I was scanned, so that's an I. And how much additional flow can be pushed through? Well, however much extra capacity we have. And so it could be as much as Bij minus Fij, but it can't be that much if there was some bottleneck earlier on, and L2 of I, and we couldn't get enough flow to I. So that's going to be a min between the excess capacity, Bij minus Fij, and how much I was able to get to I. So that's how we label when we scan a forward edge. So the other possibility is that, again, I with the same label is now has a backward edge, and this Fji is positive. Note that I need a strict inequality. And now for this edge, L1j, L2j, again, it was labeled from I, but I'm just going to keep track of the fact that it was labeled in a backward direction. And now, how much additional flow can we get? Well, no more than the minimum between L2 of I. So how much can I push through this edge and Fji? Because I'm going to have to use this edge backwards. I'm going to have to reduce its flow. So it's a very simple scanning and propagation. Every step, you just need to look at the node. It doesn't take any careful calculation or anything like that. So what does the Ford Fulkerson labeling algorithm do? We maintain a list of labeled but unscanned nodes. So in other words, once I scan S, I label its neighbors, I'm not going to scan S again. I already did that. Nothing is going to change. So this is straightforward. And I start with we initialize with the list just being node S and the label of S being plus infinity, because you can have plus infinity flow in principle come out of it. And all we do is we pick nodes from the list, we scan, label, and then we remove the picked node from the list. And we stop when the list is empty. Oops, not the empty. We stop when the list is empty. We're almost done. The key theorem tells us that if this labeling algorithm terminates, then we're at an optimal point. So if the Ford Fulkerson labeling algorithm terminates, then we are at an optimal solution. And let's just quickly say this, and then we will stop for the day and pick it up next time. So the proof of this is the reason that I introduced max flow min cut duality. So what happens when Ford Fulkerson stops? Some nodes are labeled and some are not. Some nodes are labeled, and by definition of the algorithm, S was labeled, and some are not. So W is, let's call W the labeled nodes, and certainly S is in those, and W bar is unlabeled. And note that for any ij, if I is in W and J is in W bar, we must have Fij equals Bij. So why is that? If I was labeled and then there's a forward edge to J that wasn't labeled, why did we not go there? Well, we didn't go there because it must have been that this edge was saturated. If there was a forward edge from W to W bar, we would have labeled it if it weren't saturated. So therefore, it must be saturated. And by the same token, if I is in W bar and J is in W, then Fij must have been equal to 0. Otherwise, we would have labeled it, again, by that slide two slides ago. So that means that not only is W bar a cut, of course it's a cut, any subset and its complement forms a cut, but it is a cut that satisfies complementary slackness with F. Therefore, it must be optimal. So is an optimal cut. In other words, a min cut. Hence, it's a certificate that our flow F is optimal. So in other words, Ford Fulkerson will either find an augmenting path, which means that we can use it to augment F, or it does not succeed in finding an augmenting path, in which case it's a certificate by LP duality that we are already at an optimal solution. So there's an interesting but pathological issue that happens when we don't, that could lead to non-termination, and I'll address this in a separate lecture that I'll post for those that are interested. But basically the result says that when we have rational data, the Ford Fulkerson algorithm terminates in finite time. So there's a bad example if we have irrational data, and I'll explain that in a separate video. But the reason that I want to state this, and we'll stop here, is that Ford Fulkerson is replacing the simplex algorithm. So remember that in Primal-dual, look back at that when we first introduced a general framework, we're using simplex algorithm. But here, we're actually using Ford Fulkerson in order to find F bar and to update, to find our dual solution. And therefore, our finiteness result for Primal-dual doesn't immediately port over here because we're not using the simplex algorithm. Again, I urge you to look back at that lecture where we showed Primal-dual is finite and see that we relied on properties of the simplex algorithm and the fact that it goes from BFS to BFS to argue that it is finite. When B has rational data, it's straightforward to show that Ford Fulkerson also terminates. But I'll leave the statement for there. And what we're going to do in the next lecture is use Ford Fulkerson to show that for the shortest R arborescence problem, we can solve what's known as the separation problem in polynomial time. That means we can quickly find a violated constraint if there is one, even though there's an exponential number of potential constraints. So we will pick that up in the next lecture.